Hey guys, Miss Marusik here, and in this video we're going to talk about comparing lattice energies. What kind of factors would we need to take into consideration when trying to decide which ionic compound might have the greater or the smaller lattice energy in comparison to others? So with that said, just as a little bit of a refresher from last video, lattice energy is the energy it takes to take an ionic compound as a solid and break it up into its cations and anions as a gas. So again, those two ions would have a charge associated with them, and they would be as a gas, so not in their natural state, which is a little bit different than what you might have originally thought. So with that said, we also talked about the fact that if this ionic compound is held together really strongly, if it has really strong attractive forces, then it's going to take us a lot more energy in order to break it up into its ions than it would, say, if it was held together more weakly. So surprise, surprise, look what's come back. Everybody's favorite, Coulomb's law. We're going to see Coulomb's law pop up all the time in AP chemistry. So it's kind of one of those things we just want to get used to seeing to help us justify all kinds of various phenomenon that we see. So as a reminder, our force of attraction is equal to charge over distance. Now with atoms and ions, we talked about like the charges, we looked at effective nuclear charge, distance, we looked at occupied energy levels. The occupied energy levels is still going to kind of stay with us. But for charge now, because I'm not trying to compare the attraction between protons and valence electrons, but rather here the attraction between one ion and another ion, I'm going to be talking about charge in a totally different way. This time I'm actually going to be talking about the charge of these cations and anions. So as a reminder, if I have an increase in this attractive force here, I would have an increase in lattice energy. It would take more energy to break apart those ions. So let's look at these two statements here. The first statement says, hey, as the magnitude of the charge of ions increases, meaning as I go from +1 to +2 to +3, or hey, even from -1 to -2 to -3, as that magnitude, that number of the charge increases, what happens is if that charge goes up, forces of attraction go up. And if forces of attraction go up, then look what happens to lattice energy. Our lattice energy will increase. Okay. On the flip side, now we want to be talking about the distance between our ions versus the distance between the nucleus and the electrons. So notice here it references a term called internuclear distance. So again, that is the distance between two nuclei of neighboring ions. And obviously the bigger that the electron clouds are, the greater that distance between those nuclei would be. So electron clouds are still going to kind of play a role here. So it says, hey, as the internuclear distance between two ions increases due to increased ionic radius, so we'll talk about that here in a minute. If that distance goes up, now if that gets bigger, force of attraction gets smaller. And if force of attraction gets smaller, that means lattice energy also gets smaller. So here the lattice energy would decrease. Now, I want to preface this by saying, if you don't necessarily have the data for internuclear distance, you can approximate that based on the same kind of idea that we did last unit in thinking about occupied energy levels. Obviously, the more occupied energy levels that you have, the greater the electron cloud distance, that ionic radius would be. And so if the radius of the ions themselves are bigger, then those nuclei are going to be a greater distance apart. We just have to make sure that we're being very careful to talk about the internuclear distance and not only just the ionic radius itself. Okay, so with that said, there are some example problems down here that I want to give y'all kind of a chance to process through. Normally I do this as kind of an inquiry in class, and so I want to give y'all a chance to see if you can answer these questions based on some data that you're asked to evaluate. So first, what I want you to do is there is a data set here for the group 1 chlorides. So all of them have chlorine in it, so the anion is going to be consistent, but you notice that all of them have a different group 1 metal in front of them. And you notice they all have different lattice energies. So what I want you to do is to pause this video and take just a moment and see if you can answer these first 3 questions. So again, pause the video here and go answer those first 3 questions. Did you pause it? Did you do it? I'm going to assume that you did. So let me put up here what I put down for my answers, and you can see if you had something super similar to this, okay? So first off, I said, hey, and asked what happens to lattice energies as we move down the alkali metals. Well, as I go down group 1, this is going from top to bottom on the periodic table, I see that my lattice energy values decrease. So it asks, hey, what happens to internuclear distance between ions and attractive forces as we move down the alkali metals? So here's where you kind of want to think about those occupied energy levels. As I go down a group and those occupied energy levels increase, what that means is that those internuclear distances between our ions would also increase. As I get more energy levels kind of blocking the pathway between those two nuclei, that distance is going to increase. And as we just said a minute ago, when that distance increases, our attractive forces will decrease. So it then wants us to make a concluding statement that relates internuclear distance and lattice energies. So I said, hey, as internuclear distance increase, the lattice energy values will decrease. All right, so with that said, let's now look at our second set of data down here. Now here what I see is that I have some data for some various ionic compounds, and at first I don't notice any kind of trend or anything between them, so we may just need to answer the questions for that. And then I also see our lattice energy values given. So what I want you to do is, yet again, I want you to pause the video and take a few moments and see if you can answer these bullet point questions that are below. So again, pause the video, take a couple minutes to answer them. All right, did you do it? I'm going to assume that you did. All right, so let's talk about what I put for my answers here. Oops, I moved that up a little too high. So here's what I said. Okay, first off, it said, hey, sodium and magnesium are both in the same period, yet they have different ionic charges. Compare the magnitude of ionic charges. Well, they both have a positive charge, but the magnesium has a +2 charge, whereas the sodium is only +1. So magnesium has a larger magnitude of charge. So then it wanted me to compare the lattice energies of NaCl, sodium chloride, and MgCl2, magnesium chloride. And when I go to my data over here, I see magnesium chloride has a much bigger value for the lattice energy than NaCl does. Okay, so then it had me compare another two compounds. It said, hey, why don't you compare NaCl and Na2O? Compare both their magnitude of charges and the lattice energies. Okay, well, they both have sodium in it, so those are both +1. So that's not really any different as far as the magnitude of charge is concerned. So then that's where I start looking at the second element. I notice chlorine has -1, whereas oxygen is a -2. So what that means is that here, because of that oxygen being -2, that gives us a larger magnitude of charge existing with this compound than I do with NaCl. And not only did it have a larger magnitude of charge, but when I actually go and compare their values, the 788 to the 2,570, I can see that Na2O has a much larger lattice energy value. So I made my concluding statement here. As the magnitude of ionic charges increases, the lattice energy values also increase. And I can see it does so in a pretty dramatic fashion. I know they didn't ask about it here, but look at this last one down here, Al2O3. We know aluminum has a +3 charge and oxygen has a -2 charge. So those have pretty decent magnitudes of charges. And look how high that lattice energy value got in comparison to all of those other ionic compounds. It takes a lot of energy to break up aluminum oxide. It's kind of crazy how much that increased. So the next question asked, hey, looking at both data set A and data set B, do we notice more of a lattice energy difference with changes in distance between ions, so that internuclear distance, or do we notice more difference with magnitude of charge? So if I go compare the data in the table, the first data table, I noticed some differences kind of ranging from 834 to 657, so, you know, all in the hundreds range here. But when I look at this second data set where the charges were different, look at the wide range of lattice energy values we saw there. We saw from 788 all the way up to 15,000. So what that means is that changes in magnitude of charge has a greater greater impact on lattice energy. Now, there's a saying I like to use for this. I use the saying that when I'm thinking about lattice energy, that charge trumps distance. What that means is that the charges are way more important, those magnitude of charges, in determining what my lattice energy value is going to be than our internuclear distance is going to be. So what that means is if I'm trying to compare some compounds and make a prediction on what I feel like might be the larger lattice energy or the smaller lattice energy, I'm always going to look at charge first. Okay. If I can't find a difference with charge, then I can go and look and see if there's some difference with internuclear distance. But I always want to check my charges first. So with that said, let's go ahead and flip to the second page. And on this page, what we're going to do is we're going to be comparing two compounds, and we're going to try and decide which of these compounds has the higher lattice energy. We're also going to be writing the lattice energy reactions that these compounds would have. So with that said, the first one they give us is NaCl versus AlCl3. So I'm going to start off here with writing my reactions, NaCl, and it's going to be a solid. And what I want to do is I want to break it up into its ions. So into sodium, I know sodium's in group 1, so that's going to have a +1 charge. And we are going to be breaking these up into gaseous ions, because that's the definition of lattice energy. And then our chlorine will be a -1 because it's in group 17, and that will also be a gas. All right, so now I'm going to do the same thing for the AlCl3. So I'm going to start it off as a solid. Now, aluminum being in group 13 as an ion is a +3 charge, which is the reason why here back in this compound we saw 3 chlorines. The whole idea, remember, of an ionic compound is to get charges to balance so that electrons lost and electrons gained are equal. So I'm going to show that I have 3 chlorine -1 ions here. And again, they'll be a gas. So, as I said a minute ago, charge trumps distance. So I want to check for differences in magnitude of charge first. And I see, hey, chlorine, those ions have the same charge no matter which compound they were in. But the sodium and magnesium have pretty significant charge differences. So if I want to pick the compound that had the higher lattice energy, remember higher lattice energy would be stronger attractive forces, and stronger attractive forces would mean that I want the substance that had a higher magnitude of charge. Well, in this case, that would be the AlCl3. All right, let's do another one. I have lithium fluoride versus lithium chloride. So again, I'm going to write my two reactions here. LiF as a solid. Lithium is in group 1, so I'd have lithium +1, gas. And my fluoride, -1, also a gas. And then I'm going to do the same thing for the lithium chloride. And it's going to look pretty much the same equation-wise. The only difference is that instead of chlorine, I'll have fluorine. But they're both in the same group, so they'll both have the same charge to them as those ions. So here's the deal. Lithium's obviously the same ion, so that has the same magnitude of charge. Well, these two ions also have the same magnitude of charge. So what that means is I can't use magnitude of charge here to justify which has a higher lattice energy. So this is now where I'm going to have to think about that internuclear distance. And as a reminder, if I want a higher lattice energy, what that means is I need stronger attractive forces. So that means I need the thing that has the smaller internuclear distance. Now, having a smaller internuclear distance would mean that I'm looking for something that has less occupied energy levels to it. So if I go compare chlorine and fluorine, I see they're one on top of each other here, but I see that the fluorine has less occupied energy levels to it. It only has 2 occupied energy levels, whereas the chlorine would have had 3. So therefore, my winner here is going to be the lithium fluoride. Again, because that fluoride had less occupied energy levels, which means the nuclei between lithium and fluoride would be closer together than the nuclei would be in the lithium and chlorine. All right, so here's what I want you to do. There's one more on here. I want you to pause the video for just a moment and go see if you can try it out. Did you pause the video? Did you try it out? I'm going to assume that you did. So let's go ahead and check it here. I'm going to write my two equations. I have potassium oxide here as a solid that will break up into two potassiums, each with a +1 each because they're in group 1. And an oxygen -2. And then I have potassium fluoride down here, breaking up into potassium +1 and fluoride -1. All right, I see that they both have potassium in it, so those are going to be the same. However, these two ions here I see have a different magnitude of charge. And I always want to address magnitude of charge before I address internuclear distance. So if I'm looking for the higher lattice energy, that means again I'm looking for the substance that had the higher magnitude of charge. Which means therefore that you should have selected K2O as your higher lattice energy there. It's going to take more energy to break apart the K2O than it'll take to break up the KF. How'd you do? Hopefully you did okay, right? Now there's actually one more application to lattice energy. We can actually see the implications that this would have on melting points. Now, as a reminder, melting, that process is where I'm starting to weaken forces of attraction within my structure. Now, for covalence, we're trying to break up IMFs with that. But for ionics, I'm actually trying to weaken the bonds. And so if I have a higher lattice energy, then what that would mean is that it's going to take me more energy to weaken those forces of attraction and to slowly but surely start to get it to melt. So even though this lattice energy is not the energy I would need to melt, it's different, it is related to that idea that if I have a higher lattice energy and higher, stronger attractive forces, that means I would have a higher melting point as well. So looking here, it wants us to explain why sodium fluoride has a higher melting point than sodium iodide. Well, let's compare the two for just a minute. NaF versus NaI. Both of them have sodium at +1 apiece, and then they have fluorine at -1 and iodine at -1. And so I see my magnitude of charges are the same. So what that means is I must be trying to reason this out with thinking about internuclear distance here. So in thinking about my sodium fluoride, I know that fluorine -1 has a lesser number of occupied energy levels than the iodide. And so if that's the case, then what that means is that NaF has a smaller internuclear distance. Oops, nuclear, there we go, internuclear distance than the NaI does. And if that's the case, then that means NaF has stronger attractive forces, which is why we have the higher melting point. So I can do the same thing on the other one. It says, hey, explain why CaF2 has a higher melting point than NaF. So let's compare the two for just a second. CaF2, calcium's +2, fluorine's -1. I always check those charges first. NaF, sodium's +1, fluorine is -1. I see they both have fluorine in them, but yet again, I see here calcium has a +2, where sodium only has a +1. And so I don't have to worry about occupied energy levels here because I can reason this one out with that magnitude of charge. Calcium plus 2 has a higher magnitude of charge than the sodium plus 1. And so therefore, what that means is that calcium fluoride has stronger attractive forces. By the way, you may have also noticed that they mentioned on here solubility in water. And if you kind of look here, the thing that had the least number of occupied energy levels, comparing fluorine and iodine, and yet the highest magnitude of charge at calcium, the thing that had both magnitude of charge and occupied energy levels more favorable was insoluble in water. One of the things that does play a role in solubility are attractive forces. It's not the only thing that plays a role, but it's one of the major things that plays a role. And so what happens is that in order to dissolve, you need to make sure that the attractions to water are strong enough to be able to pull apart the attractions of calcium fluoride. That the new attraction I'm forming between the ion and water, the ion dipole attraction, is stronger than these original ion forces that we have. And so if the forces are too strong, then what happens is the water can't pull it apart. It doesn't have enough attraction to be able to loosen that original attraction that existed. So we'll talk a little bit more about that when we get to solutions and to solubility and all kinds of good stuff, but to kind of give you a little preview there for the future. All right, hopefully you're feeling more confident with being able to identify what substances would have a higher lattice energy or lower lattice energy than another. If you have any questions or need any help, please feel free to email me. Bye, guys.